Hello everyone and welcome to Kiru's online lectures. I am Kira Jhamtani and today's topic is Aldehydes, Ketones and Carboxylic acids part 3. In part 1 we studied introduction, nomenclature, structure of carbonyl compounds. In part 2 we studied preparation of aldehydes and ketones. Now in part 3 we are going to study physical and chemical properties of aldehydes and ketones. So starting with physical properties of aldehydes and ketones, methanol, it is a gas at room temperature. Ethanol, it is volatile liquid. Other aldehydes and ketones, they are liquid or solid. If we talk about their boiling points, so their boiling points are higher than hydrocarbons and ethers of comparable molecular masses. This is due to the reason that the weak molecular association in aldehydes and ketones arises out of dipole-dipole interactions. Next is boiling point of aldehydes and ketones. These are lower than alcohols due to the absence of intermolecular hydrogen bonding in aldehydes and ketones. Lower members, coming on to the solubility, lower members of aldehydes and ketones, they are miscible with water in all proportions because they form hydrogen bond with water. This solubility, if we talk about solubility, this solubility decreases with increase in alkyl group. All aldehydes and ketones, they are fairly soluble in organic solvents like benzene, ether, methanol, chloroform, etc. Lower aldehydes, they have pungent odors, and as the size of molecule increases, this odor becomes less pungent and more fragrant. And therefore, the naturally occurring aldehydes and ketones, they are used in the blending of perfumes and flavoring agents. Now, moving on to the chemical properties of aldehydes and ketones. So, first of all, we'll learn the mechanism. So, the first chemical property is nucleophilic addition reaction. So, in mechanism, the nucleophile, as we are performing nucleophilic addition reaction, the nucleophile attacks electrophilic carbon atom of the polar carbonyl group. So, here we have, this is aldehydes or ketones, it can be anything. So, here the first step, which is the slowest step, here the attack of nucleophile takes place. Thus, this nucleophile attacks and this O minus. So, here the nucleophile is attacking electrophilic carbon atom of the polar carbonyl group from the direction approximately perpendicular to the plane of sp2 hybridized orbitals of carbonyl compound. Thus, this hybridization from sp2 it changes to sp3 and thus a tetrahedral alkoxide intermediate is formed. Now, this intermediate captures proton, that is H plus ion, and this step is the fast reaction. This is step 2 reaction. So, this step is the fast reaction and the step 1 reaction is the slowest reaction. Now, this intermediate is capturing proton from reaction medium to give electrically neutral product. So, thus this nucleophile attacked, this A and B groups are attached over here and thus OH is formed. So, net result is addition of nucleophile. In first step, the nucleophile attacked and H plus across the carbon oxygen double bond. Coming on to the reactivity, these aldehydes are usually more reactive than ketones in nucleophilic addition reaction. The reason are, there are two reasons, that is steric hindrance and electronic reason. Now, coming on to steric hindrance, what is steric hindrance? Sterically, the presence of two large substituent in ketones. In ketones, there are two groups, that is R, C, O, R. So, two alkyl groups are present over here which hinders the approach of nucleophile to carbonyl carbon. And as in aldehydes, only one alkyl group is present, so nucleophile can attack easily. Electronically, if we speak, so electronically aldehydes are more reactive since the presence of two alkyl groups over here in ketones, it reduces electrophilicity of the carbonyl more effectively than in aldehydes. Now moving on to the reaction. So the first is addition of HCN. This is aldehyde or ketone, it can be anything. Here the HCN addition is taking place. So first of all, nucleophile attacks over here. So nucleophile will attack. So here we'll get O minus and here we'll get Cn. Then the transfer of proton will take place and thus we'll get OH and Cn. This is how addition of HCN takes place. Then coming on to this compound is known as cyanohydrin. Then coming on to addition of sodium hydrogen sulfite. So here we have aldehydes or ketones, NaHSO3, this is sodium sulfite. So first of all, nucleophile will attack over here. The nucleophile attack will be, here it will be like this, SO3H and Na will go with ONA. Now the proton will shift over here, so proton will shift this side and sodium will go with SO3Na. So thus the formation will be, by the shifting of proton, we'll get SO3Na and OH. This is bisulfite addition compound. So this is how addition of HCN and hydrogen sulfite takes place. Coming on to next, addition of Grignard reagent. It can be anything. It can be aldehyde ketone plus RMgX. Now when Grignard reagent is attacking over here, which we have already studied in our previous videos, here MgX will go with O and R will go here. Thus the reaction will be OMgX and R. Then hydrolysis will take place. Thus this bond will break here, H and OH. So we'll get OH and R plus MgXOH. So this is how aldehydes and ketones participate in the reaction. Coming on to addition of alcohols. Now let's suppose if we have aldehyde RCHO. So addition of alcohols, that is R-OH is taking place over here with HCl gas. So we'll get RCH, OR- and here OH. Then again R-OH will react, that is one more alcohol molecule will react and we'll get RCH, OR-, OR-. This is known as acetyl and this one is hemiacetyl. Now in place of aldehydes, if we take ketone over here, so with ketone, when we react alcohol, that is CH2OH, CH2OH, so here we get RRC and thus OCH2 and here also OCH2 plus this water molecule is removed, H2O. This is known as ketyl, which is ethylene glycol ketyl. Moving on to addition of ammonia and its derivatives. So we have aldehydes or ketones when they react with ammonia. So here what happens, ammonia, like we write NH3, so it is written as H2N and one H is remain free, this Z. This is basically over here in this reaction what happens. Now this Z can be anything because we have to perform the addition reaction of ammonia and its derivatives. So if it is only ammonia, then Z is then Z is H, and if it is amine, so in that case Z will be alkyl group. If it is hydroxylamine, then Z will be OH. If it is hydrazine, then Z will be NH2, and if it is phenylhydrazine, then Z will be NHC6H5, and if it is 2,4-dinitrophenylhydrazine, then Z will be C6H5. It will be like this, NH NO2, NO2, which is 2,4-dinitrophenol, 2,4-dinitrophenol phenylhydrazine. So if Z is NHCONH2, then it is semicarbazide. So in this reaction, basically what happens here, the removal of H2O takes place. Then we get C double bond NZ. Now let's suppose if there is NH2 in place of Z, that is we are talking about hydrazine. So C double bond O, H2N and NH2. So this water removal will take place, and thus we will get over here NH2. So with hydrazine, the product formed will be hydrazone. Similarly, one more reaction we are performing. In place of Z, here if I am taking semicarbazide, that is NHCO NH2. Again, this removal will take place and product formed will be C double bond N NHCO NH2, which is semicarbazone. So this is how addition reaction of ammonia and its derivative takes place. Now moving on to the second reaction, the second chemical property of aldehydes and ketones, which is reduction. So first is reduction to alcohols. So aldehydes, if we have aldehyde over here, that is RCHO. So aldehydes, they are reduced to primary alcohols by sodium borohydride, that is NaBH4, or we can take LiAlH4, as well as by catalytic hydrogenation. If we have ketones over here, so ketones, they are reduced to secondary alcohols. Again the reagents will be same, that is sodium borohydride or lithium aluminum hydride. Coming on to reduction to hydrocarbons. Now let's suppose we have aldehydes or ketones, anything. This is aldehydes, they are reduced to hydrocarbons, that is CH2 plus H2O. Now over here, if these are reduced to hydrocarbons on treatment with zinc amalgam and concentrated HCl, so this reaction is known as Clemenson's reduction reaction. Now if the same reaction, if it is carried out by heating with hydrazine, that is NH2NH2, or with hydrazine which is followed by heating with sodium or potassium hydroxide, so here the removal of H2O takes place, and thus we get intermediate, which is amine, and then KOH followed by heating with sodium or potassium hydroxide, thus we get hydrocarbon plus N2. So if we take hydrazine over here, this reaction is known as Wolff-Kishner reduction reaction. Coming on to next chemical property of aldehydes and ketones, which is oxidation. So aldehydes differ from ketones in their oxidation reaction. These aldehydes, if we talk, they are easily oxidized to carboxylic acids on treatment with common oxidizing agents like nitric acid, potassium permanganate, or potassium dichromate. Even mild oxidizing agents, mainly Tollens reagent, failing solutions, oxidize aldehydes. But if we talk about ketones, RCOR, so in ketones, they are generally oxidized under vigorous conditions, that is, strong oxidizing agents at high temperature is needed. So their oxidation involves carbon-carbon bond cleavage to afford a mixture of carboxylic acids having less number of carbon atoms than the parent. So here basically what happens, the cleavage takes place, thus we get RCOOH plus let's suppose R 1 type 2 moles of acids we get if same alkyl group is there. So let's suppose if we are having ketone like RCH2, C double bond O, CH2R, So on oxidation, the cleavage will take place over here, and thus we'll get RCH2COOH plus RCH2RCOOH. So this is how cleavage takes place over here. Now mild oxidizing agents given below, that is Tollens test and Fehling's test, they are basically used to distinguish aldehydes and ketones. So aldehydes, on warming aldehydes with freshly prepared ammonical silver nitrate solution, that is Tollens reagent, a bright silver mirror is produced due to formation of silver metal, and this reaction is only shown by aldehydes only. So this Tollens test is used to distinguish aldehydes from ketones. So ammonical silver nitrate solution we take over here, and thus we get silver metal, that is the silver lining. This silver lining only indicates that the carbonyl group is aldehyde. So this is Tollens reagent, which is ammonical silver nitrate solution. Coming on to next, Fehling's test. Fehling's test, Fehling's reagent comprises of two solutions. The one is Fehling solution A and Fehling solution B. So Fehling solution A is aqueous copper sulfate and Fehling solution B is alkaline sodium potassium tartrate, which is Rochelle salt. These two solutions are mixed in equal amounts before test. Now on heating aldehydes with Fehling solution, that is this copper solution, a reddish brown PPT is obtained. Thus weak aldehydes are oxidized to the corresponding carboxylate ion, and here a reddish brown PPT is obtained. This reddish brown PPT indicates that the given organic compound is aldehyde. Coming on to next, oxidation of methyl ketones by haloform reaction. So we have our COCH3, basically aldehydes and ketones which have at least one methyl group linked to the carbonyl atom. These are oxidized by sodium hypohalite to sodium salts of carboxylic acids. So here the reaction is carried out by NaOX and we get a RCOONA. This bond breaks, RCOONA plus CHX3 we get. That is, if we take Cl over here, so we can get chloroform also. If we get I over here, we can get iodoform also. So this is how oxidation of methyl ketones is done. Now moving on to the next reactions. Next reactions are reactions due to the alpha hydrogen of aldehydes and ketones. The aldehydes and ketones, they undergo number of reactions due to their acidic nature, due to the acidic nature of alpha hydrogen. So the activity of alpha hydrogen atom of carbonyl compound is due to strong electron withdrawing group. So here basically what happens, if we have this aldehydes or ketones, they basically the shifting takes place. So like H goes here and then the shifting takes place, this B. So the intermediate is formed, C and C minus, and thus we get CO double bond C. This is how reaction takes place due to alpha hydrogen. Now the first reaction is aldol condensation. This reaction is basically given by those compounds, those carbonyl group which have at least one alpha hydrogen. They undergo reaction in presence of dilute alkali, that is dilute KOH, or it can be dilute NaOH, as a catalyst to form beta hydroxyaldehydes or beta hydroxy ketones. This is known as aldol condensation. Now let's suppose I have CH3CHO. Now 2 moles of we take CH3CHO. Here what happens, this is alpha carbon. Now we are taking like this CH3, C double bond O, and here it is H, plus C double bond O H CH3. So here what will happen, this H, this is alpha carbon because this CHO is a group. So alpha carbon, the hydrogen of alpha carbon combines with this O. Thus we get CH3COH, and here it is CH. Then this is CH2 and CHO. So this is alpha carbon and this one is beta carbon. So this is known as beta hydroxyaldehyde, which on heating, if we'll heat it, here the removal of H2O takes place. On heating, this OH and H will be removed. Thus the product formed will be alkene CH3 CH double bond CH-CHO, which is butyl. So this is known as aldol condensation. The name aldol is basically derived from the name of two functional groups, that is aldehydes and alcohols, because over here the intermediate which we are getting is alcohol. Therefore it is known as aldol condensation. So over here basically what happens, the alpha hydrogen shifts with the oxygen, and thus we get one intermediate which is beta hydroxyaldehyde, and if we are taking ketone, so it will be beta hydroxyketone, which on heating will form enol. That is, if we have taken aldehydes, so we will get butenol. Now moving on to cross aldol. Cross aldol condensation is when we are taking two different aldehydes. Like in previous example, we took two same aldehydes. Now we are taking two different aldehydes. So CHO plus. Now here we are taking CH3 CH2 CHO. We will take two different aldehydes, which is CH3 CHO plus CH3 CH2 CHO. So alpha carbon will be this one. This is alpha hydrogen. I will be writing over here alpha hydrogen CH, and this is CHO, and this one is CH3. So this will shift over here. Thus we will get CH3 COH CH CH CH3 and CHO. Now again the removal of water will take place. So when water will be removed, thus we will get CH3 CH double bond C CH3 CHO. Now the same product can be formed if we reverse the reaction. If we are reversing the reaction, like if I am writing over here CH3 CH2 CHO, that is C double bond O and H, and then I am writing this compound, that is ethanol. So H CH2 CHO, this H will go there, and we will get CH3 CH2 C CHOH CH2 CHO. Then again on heating, that is removal of water will take place. So this OH and H will be removed. So H can be removed from this side also, from this side also. So there will be two products formed over here. If it is removing from this carbon, we are removing H. So product will be CH3 CH double bond CH CH2 CHO, and if we are removing from this carbon, the product will be CH3 CH2 CH double bond CHO. So this is known as aldol, cross aldol condensation, in which we take two different aldehydes. Next reaction is Cannizzaro reaction. Aldehydes which do not have alpha hydrogen, so which are not having alpha hydrogen, undergo self oxidation and reduction reaction, which is disproportionation reaction, on treatment with concentrated alkali. In this reaction, one molecule of aldehyde is reduced to alcohol and other molecule is reduced to carboxylic acid. Like we have HCHO. So HCHO plus HCHO with concentrated alkali, that is concentrated OH. So one molecule will form alcohol, which is CH3OH. Other molecule will form the salt Other molecule is oxidized to carboxylic acid salt. Thus, we will get HCOOK because we have taken over here K. Now, one more compound is there which is not having alpha hydrogen, which is benzaldehyde, C6H5CHO. So, C6H5CHO reaction with concentrated KOH will give C6H5CH2OH, which is benzyl alcohol, and the salt of benzoic acid. So, we'll get C6H5COOK. Thus, here we'll get sodium benzoate, and this is benzyl alcohol. So, in aldol condensation, alpha hydrogen is transmitted. So, aldol condensation is carried by the compounds which have alpha hydrogen. Cannizzaro reaction is carried by the compounds which do not have alpha hydrogen. Moving on to electrophilic substitution reaction. So, like we have over here benzaldehyde. So, benzaldehyde, aromatic aldehydes and ketones, they undergo electrophilic substitution reaction in which carbonyl group act as deactivating group. Thus, we say it is meta-directing. So, here we are performing nitration reaction. So, nitration reaction, the nitro group will attach to the meta position. So, thus the product formed is meta-nitrobenzaldehyde. So, in today's video, we studied all the physical and chemical properties of aldehydes and ketones. Hope you guys are finding videos helpful. So, do like, share and subscribe the channel. Thank you.